So you've seen the theory, you've seen what Bayesian networks are theoretically. Let me just spend maybe 10 minutes or so to give you a few motivating examples. We'll spend the rest of the second hour on the problem of learning from data, but let's just spend some time with the software. First of all, here's where you can get the software from. Here is our website, basefusion.com. To download academic versions of the software, you follow this link. But let me show you, there's actually quite a lot of things that will support you. There is forum where you can ask questions about the software, about the methodology. There are books, there are publications based on the software, etc. Genie is very popular in academic environments because, of course, it's free, but it's also very good. People really love it. It has most of the things that have been developed theoretically are there and implemented very, very well, very fast. Documentation, you can look at all the documentation from this site in HTML, PDF format. Genie, then the Smile and Smile wrappers, if you want to program and use it. There's some introductory materials and other documents. Here's where you get Genie from. You go to Downloads, and academic downloads are on the right-hand side. Business downloads, there's a 30-day evaluation version, but it will stop working after 30 days until you purchase the license. But academic versions are free, so you can follow this link. And you will need to log on using one of your social media accounts. We don't do anything with it. It's just a way of verifying that people who download who they are. We can then detect abuse of academic licenses and also make sure that bad actors don't get the software. And here's where you download it, and you can, after downloading, you can install it. You can get a 6 months license for Smile by just clicking this button. If you need a longer license because of your research work, do contact with us. We can issue a license for a longer period of time. Great. Genie. Genie is essentially a program that has been written for Windows, but it runs successfully on Macintosh and on Linux systems under wrappers. It's a developer environment for models. You can develop models by just, let me maybe make the font a little bigger, by just clicking on the screen, and that drops a variable on the screen. You can call this variable disease. You can have another one test. You can connect them. Once you have them, you can double click on the nodes, edit the names, present. I don't want to spend much time. You can enter probability distributions. You can also do it graphically. In general, creating nodes, their distributions, you will see that there is a conditional probability distribution because this node has one parent, and you can build models interactively. Let me show you a couple of models that you can download from our repository. I didn't show you that, but there is actually a repository which you can get to from our home. One of the support links, there is an interactive model repository that allows you to play with models interactively without installing anything on your computer. There is over 100 different models in the repository, and you can work with them as you would with Genie almost, but you cannot edit them. So if I want to observe a value of, let's say, severe headaches, I can go here and click on this state. That amounts to observation. It's observed. The probabilities are updated. I can observe comma. I can do it also by right-clicking, set evidence present. The network updates. So you can do it here. But in Genie, you can also download any of these models by clicking on this box icon. Now I'm connecting to our repository and browsing through different models, and I can download the model from here. Let me actually show you, just to impress you, let me show you the locomotive model that you saw was very large. I'm now scrolling with the mouse, control mouse. You see, this is the spaghetti model that I showed you. It is indeed like a spaghetti. Updating this model takes just a fraction of a second. Let me show some of the disease nodes. Machine fault. Where are they? I saw them here. Here they are. So let me make the nodes bigger to show you the time it takes to update. Question mark, the node is not updated. Updated already, 2100 nodes. Speed is practically not a problem anymore. Let me show you some of the things that you can do with the joint probability distribution in addition to just Bayesian updating. Bayesian updating is, of course, you observe a value and you calculate the posterior probability distribution. Observe or unobserve it, it will change the distribution. Because we have a joint probability distribution here, we can calculate things like strength of influences. So you can calculate based on the numerical values in these nodes how strong this influence is. That's illustrated by the thickness of the arrow. Simple but cool thing. Also, this is a diagnostic model. It's a model for diagnosis of liver disorders. We can use a special diagnostic interface that pulls out all of the diseases here, all of the observations made. I made one, as you remember. And here are all the possible observations that you can make. They are rank ordered from the most to least informative. If I want to learn something about this disease in red, here is the most informative test, or just a simple observation of the biological of sex of the person tells me the most about this disease. If I observe something that is here, doesn't change much, right? So all of you have the experience of calling a call center to get help with your computer, the TV, or whatever, and they start asking you stupid questions, really stupid, that don't make any sense. When you have something like this, the order is dynamic. Depending on the things that I have seen, here are the most informative things to know, to ask about, because they will tell you most about this distribution. These things doesn't make any sense to ask about. And the order on this list changes. It's all computed from the joint distribution using a measure known as cross entropy, mutual information. We can do differential diagnosis. I want to know a test, an observation that makes most sense, that will be most useful in distinguishing between these four. Let me clear all of this. Start with a new patient. Here are the 4 diseases I'm interested in. Sex would be a good thing. You see, it shot them apart. Cancer was pretty much, not excluded, but became much less likely. When I observe this, again, variable observation, it looks like PBC is present. Again, I should probably continue with testing and doing things until I make this really very likely. Is this enough? Whatever. So here are just a couple of things that you can do with joint distributions. You can calculate a lot of things. This basic calculation, which is observing a value, setting an evidence. You see the probability is updated. That's the basic updating of probabilities, but you can do much more. I promised to show you let me show you the qualitative Gini. It is installed with Gini on your disk when you install. If you don't know how to find it, go to the program files Gini directory. You will see also QGini. QGini is a qualitative Gini. Let me load a model from the repository. Here is what it is. We have a model that is specified by a very small number of probabilities. For every node, there is a probability, and for every arc, there is a probability, telling us about the strength of this connection. Every node and every arc has a number, so very small number of numbers. And now what can we do? We could very quickly build these models and very quickly project them on the wall in a group setting, and we could together look at what happens when this is a model for an airplane manufacturer. And what will happen if the client wants the plane to carry more load? You see the colors changing. You see how these observations propagate through the model, and you saw also profits to get a little bit lighter. Dark green is very good, dark red is very bad, and green means that there will be profits, but not as high as originally when the client didn't want the airplane to be faster or carry more load. You can even do things like, not here, sorry. Here it is. This is also the calculation of the mutual information. If you designate nodes to those that you could manipulate or observe, you also will see the effect of manipulating something, the effect on the target, on the profit, the focus of the inference, or observations. So again, the calculations are purely from the representation of the joint probability distribution. Since we are here, let me show you a dynamic model. So this model is dynamic, equivalent to a system of difference equations. Some of the links are temporal links, means that in this case, aggressive advertising will influence sales with a delay of 1. It takes time for the effect to happen. Reputation of our product is influencing itself, it's propagating itself, but also with a delay. It can influence the company's reputation, but with a bigger delay of 2 time steps ahead, equivalent of the second differential. So now what can I do with this kind of model? I can perform inference. Let me view temporal beliefs, which is essentially a picture of probabilities that I want to see. I want to see the reputation of the product, market share, profits is a good thing to see, maybe company's reputation. These are the things that I'm interested in. If I now make observation or change something, suppose I decide in the very beginning to build a poor quality product. Here's what will happen over time, over 24 steps, say 24 months after introducing the product. In the beginning, the product is going to be believed to be good from our company, similar to our reputation. But over time, as people realize it's a poor quality product, the reputation will go down slowly to some value. What if we advertise a lot? It will help a little bit, but not a lot, right? You see that. What if we build a high quality product? Looks a little bit better. So this kind of, qualitative inference over time. And that's done with Bayesian networks. You can export these models to Gini and develop them further in Gini. Finally, I promised to you just a short motivating introduction. What if you have data? Suppose you have let's see, I don't see the, let me open it here. On my second screen, I wanted to open a data file. I'm almost there. Please bear with me. So here is an artificial data set, but pretending to be a real data set. Imagine that this data set is collected in a bank. Let me actually make it larger and show you what it shows. So there are variables in the columns. Every column is a variable. We measured clients. Every row, every record is a client. We measured the client over several criteria when the client applied for a loan. So we asked about payment history, work history, income, assets, profession, age, etc. And then we had a chance to observe whether this client paid back the loan or not. We are interested in learning what causes people not to pay the loan or to pay back the loan. The magic is that you could, from this data set, you could learn a model. Let me learn a model. Takes a fraction of a second, and I'm learning the interactions between variables in this model. If you look at the data, probably you will notice that there are a lot of dependencies, but these dependencies are not immediate. They are through common causes or other variables. I'm learning the structure from using this learning procedure. Let me proceed, learn the parameters, and go to the screen. Let me maybe make them a little bit larger so that we can see the names. Maybe let me see them also as bar charts so that we can see the distributions. Let me update immediately and make them a little bit larger still. Maybe too large. Okay, let me go back to see them as icons to show you something. Now I see the structure of the model. I can also see the strengths of interactions. I have just learned them. I have learned the structure and the parameters of this model. Now I can go to any of these nodes, and the probability tables are learned from the data. Conditional probability tables. Sometimes they are large, they are exponential in the number of parents. You see there are many columns here, and they are learned from data. So now what can I do with that? I can use it, right, in addition to the insight that I get from learning that, causal insight, I can also use it immediately as in a decision support system. I want to predict this, and here are my possible input variables. A new client comes to my bank, and I can ask, what is your income? What are your assets? What is your age? And as I enter these things, please note that the probability of this person paying back the loan changes. I can have a threshold probability that this person will pay back the loan, a threshold above which I will give the loan, otherwise I will not. So I can use it in making a decision. I have a model that is immediately usable and that was learned purely from data. So that was the magic I wanted to show you. I will go over to slides to show you the theory behind learning in a moment. One more thing I wanted to show you. These models that contain continuous variables. So here's that model for heating and cooling. I can imagine that in risk analysis, reliability risk analysis, you have a lot of continuous variables, equations, etc. You can work with them using Bayesian networks. There's no problem with it. And this is a hybrid model. If you look at variables like this, they are defined by means of an equation. Essentially, three variables coming in, three parents, they are used in the equation. You can easily add noise to them. There is no limitation on the equation. So some systems will allow you to work only with linear equations, not Gini. Gini will allow you to put anything you want, any of these functions. So we have quite a number of random number generators. We have statistical functions. We have arithmetic, combinatorial, trigonometric functions. Any of these functions you can use in the definitions. Because there's no limitation on the definitions, whatever is happening in the world, whatever your engineering economic knowledge is, use it in the model. The only algorithm that will work reliably is stochastic sampling, so simulation. And this is the algorithm that was used to derive those marginal probability distributions. When we observe nodes with parents like this, what happens is Gini converts the continuous network into a discrete network, but it's up to you how you discretize it. And as you see, you can also get some insight about the continuous distribution by working purely with a discrete distribution. The reason why we have to do it is that theoretically, inference in continuous systems of equations is hard when you observe something that has ancestors. That's the only reason, but otherwise, this is just temporary discretization. Nothing has changed in the definition of this variable. It's still what it was. It's just that the program automatically discretized, derived conditional probability tables, and which you can use in discrete inference. Do you have any questions so far about Gini? I wasn't planning to come back to Gini for too long, unless you have questions. So, do you have any questions at this point?
If anyone has any question, feel free to either type it or unmute yourself.
Well, you will be able to download it and play with the ideas, with the example models. You can construct your own models and perhaps use it in the problems that you are working with, which are, I'm sure, very interesting problems. So you can always become a Gini user, and if you have questions, you can always ask them on the forum, and which we monitor, and you get the answers fairly quickly, I think. If there are no questions, let me now go over to the last part of the meeting. We only have half an hour, but so not a lot. But I just wanted you to understand the foundations of learning, because it looks like magic. I want to assure you that this is good statistics, good science that we are doing. So I wanted to show you a few slides on the theory, how it works. First, before we go into the slides, let me show you, just play with a little bit of ideas, with a few ideas, the relationship between probability and causality. There is actually an axiomatic way of capturing that. There is an axiom, assumption, known as causal Markov condition, but it's quite possible, quite easy to understand that relationship, the consequences of that axiom in practice. And most of the graphs that you will see here on the screen are causal. I will be making it explicit when it's not causal. The first thing in the relationship between causality and probability is that causal relations result in dependencies. So flu is a causal factor in fever. Fever is a causal factor in shivering. There are other causes of fever. There are other causes of shivering. I just have this small model in my modeling panel. Dependence. When I observe shivering, I'm just double-clicking on this state. Please note that the other two variables will change. When I observe flu, the others will change too. Probability of fever will go up, and shivering will also go up in probability. When I observe fever, the other will change too. That corresponds to our understanding of this system. That's, of course, mathematics, capturing the joint distribution, but that corresponds to the understanding. Whenever you have a chain of influences, everything on that chain is going to be dependent on one another. Simple rule that has been known for centuries, really centuries. Sometimes there are correlations or dependencies that we have a harder time understanding. There's a strong relationship between ice cream consumption and drowning. When there was a lot of ice cream consumed on Newfoundland, I'm quite sure, that there were more drownings than on other days. When there was very little ice cream consumed, then there were also fewer drownings. A lot of ice cream, more drownings. Little ice cream, fewer drownings. What's the explanation of that? Here's, I think, what a good causal structure of that could be. The outside temperature is a common cause of ice cream consumption, swimming outdoors to cool off, and when people swim in unguarded places, sometimes, hopefully not too often, they drown. You see the same dependence that you saw on the previous picture, but you see the mechanism of the dependence. A general rule: common causes result in dependencies. That's been also known for ages, really for ages. People have known it, that common causes have to be controlled, conditioned on, in order to get rid of the dependencies. If you condition on this, then you can eat. So you are looking at warm days only. You can eat as much ice cream as you want or as little as you want. It will have zero influence on drowning. Conditioning breaks that connection. Just as conditioning in a chain breaks the connections on the chain. If, let's say, we put a police person on every open body of water, we are saying that there will be no swimming outdoors, the police will forbid it, then you can eat as much ice cream as you want. The day can be as warm as you want. It will have no effect on drowning. I have cut this connection by conditioning, made the things independent. That's another thing that is happening with causation and probability. This is really a joke on my part. You hear that it's good to have some wine regularly, a glass of wine a day. It will influence your heart. It will produce lower probability of heart disease. If you don't drink, probability goes a little bit up. Here is my explanation of that. Life enjoyment. People who enjoy life tend to drink more because they don't work in the evening like graduate students do. And they also, because of being relaxed and not having too much stress, they also have healthier hearts than people who are a little bit tense. Now, this common cause makes the two dependent. If this is indeed the graph, then you can drink as much wine as you want. It will not impact your heart because you are either a person who enjoys life, please note that drinking makes no difference for heart disease, or doesn't enjoy life, doesn't influence that, right? It's a joke, by the way. I think that there is some direct influence of alcohol on heart.
But there is a question for you, Marek, from one of the students.
Go ahead, please.
He's asking why, when the drink was 100%, heart disease was still no.
This is, of course, a simplification of the real system in the world. I have a variable wine consumption, and by drinks I mean drinks in moderation. Abstains means drinks nothing. I don't know if this was the question. You could easily model this variable by a continuous variable that denotes the exact quantity that the person drinks. or a discrete variable saying 1, 2, 3, 4, 5 consumptions a day, or 0, right? Has this answered the question? Was this the question?
Yeah, it was from one of the students. Yeah, I thought it was just mentioned. Yeah.
Anyway, please don't hesitate to turn on your microphone and just speak up if you have questions. There is a known correlation between, as you know, you can get statistics of surgeons, at least in US. You can, for any surgeon that may be planning to operate on you, you can check their statistics, the death rate in operations, success in operations. So it turns out that top surgeons have actually worse statistics than average surgeons, as you see here. What is the explanation of that? Here is a possible explanation. I think this is the correct, true explanation of that. You see the same correlation. But if you look at difficult cases, which go very often to top surgeons, they also have higher probability of death. In those difficult cases, top surgeons have twice as low death rate than less experienced surgeons. In easy cases, the same thing happens. Top surgeons have better statistics than average surgeons. But just through this common cause, top surgeons will have worse statistics than average surgeons. So these two things, common causes and chains, were understood for centuries, as I said. There is a third thing that was discovered only in 1970s by a German statistician, Nanny Vermuth. She noticed that, she actually proved it, when you have a joint distribution such that two variables influence a third variable, and they are independent a priori, they become dependent when you condition on this variable. So let's actually get this model right away. Here are 4 different causes of problems in marriage: drinking, addiction, unfaithfulness, and strong emotional dependence on parents. They may be independent on one another. A person who is addicted is not necessarily unfaithful. A person who is unfaithful is not necessarily addicted. They are independent in this model. But when I observe marital problems, please know that all of them became more likely, because after all, something must have caused those problems. Here are 4 possible causes. They become dependent. When I learn that Bob is getting divorced, and then I learn he's been drinking before, during, and after the wedding, please note that observing drinking, which is a plausible explanation of the marital problems, makes addiction, unfaithfulness, and strong emotional dependence on parents less likely. This is, of course, conditional dependence. When I condition on something, things become dependent. It is intuitive for humans because we do this kind of inference all the time. But it was only recently that it was discovered that probability theory correctly models that. So you see a correct probabilistic model, a joint probability distribution that correctly shows that happening. A caution for all those who do learning from data, any data analysis or learning. You must have gotten many cautions of that. And we know that heart problems and lung problems are strongly dependent in intensive care units. Negative dependence. People with heart problems tend to have lower probability of lung problems than people with no heart problems. What is the explanation? The numbers, by the way, I put them here, but the qualitative phenomenon of dependence, positive or negative, is there. I show you real examples. What is happening here is that heart problems and lung problems are 2 important causes of being in a hospital intensive care unit. Because you die if you have heart problems, so they immediately bring you to an intensive care unit to watch you. The same lung problems. If you stop breathing, you die. Of course, in this model, they are shown independent, but maybe they are dependent depending on existing diseases, on the age, etc. But I just wanted to demonstrate something. So they are independent. But now, if you collect your data in an intensive care unit, you will notice that they become dependent. So a word of caution, every data that is ever collected is conditioned on something. It's collected somewhere. It's very important to reflect on where it is coming from, what it is conditioned on, because you may get induced dependencies that were not there in the original system. Here are just more complex examples. Causal model, two diseases that cause increased bilirubin level in blood. Bilirubin, when it's increased, causes jaundice. Jaundice is a kind of discoloration of the skin between gray and yellow, really sickly color of the skin, because bilirubin deposits under the skin, and you can see it in a patient, regardless of the tint of your skin that you had to start with. It just doesn't look very good, very normal. Increased bilirubin can also lead to lethargy. So two effects of bilirubin, two causes, and then another effect of hepatitis B. And you can see all of these things happening. If I observe, say, lethargy, there's a chain of influences. So hepatitis B will change, bilirubin will change. Chain to here also, common cause between these two, common cause between these two. So everything is changing. When I observed increased bilirubin level, now I have broken this common cause, so lethargy tells me nothing about jaundice. And now liver cancer and hepatitis B become dependent. See? Because if I observe cancer, I have a plausible explanation for bilirubin level. Hepatitis B becomes less likely. Practically, in a situation like this, people may perform an antibody test for hepatitis virus that provides evidence for hepatitis B, makes the probability of cancer less likely. So you see all three. You see chains, common causes, and you see conditional dependence. These are three important consequences of Markov condition. And now we are ready to talk about learning those structures. We have really very little time. We have just 15 minutes. So I'm not going to be able to present everything to you, but we can do two things. We can go over, and those of you have to go, you go, and there will be a recording of the whole thing. Or I will present you the most important things and just go quickly. What I want to do is I want you to understand the mechanisms that are happening in learning Bayesian networks from data. So we can do this magic. We can learn structure from the data. Practically, we have a set of variables. We have simultaneous measurements of those variables. I mentioned that. We can learn the structure that gives us insight, or we can learn the whole distribution, and then we can use the model for support or anything. Why are we interested in causality? Causality allows us to predict the effects of manipulation. It's a fundamental thing in science. Scientists want to know the causal structure. Most experiments that we do focus on discovering causality. And of course, when you construct models, people tend to think in causal terms, so it's easier to build causal models. Of course, the two go together, so they are not surprising that they go together. I'm going to go sometimes really fast. So I just wanted to say here that in statistics, the word causality was pushed out in early 20th century. It's making a strong comeback. So if you look at modern books for statistics, you will see more references to the word causality. Because they pushed out the word cause, they invented many other terms that you probably have seen in the textbooks. In experimental design, which is what scientists are doing, conducting experiments, you want to establish or disprove causation, so you cannot really juggle with different terms. You really need to think and talk about causality. So it's important to know the relationship, and I have demonstrated it very informally to you. Causality and probability are related. When you have a causal structure, what you will do is you will observe dependence in data that you see in life. In the data, or when you walk around, you will see that people who have flu tend to have more fever than people who don't have flu. Important thing is causes don't have to cause the effect, so they are not necessary and not sufficient to cause the effect. It's all uncertain, of course. There are many other causes of fever, and there are people who have flu and don't have fever, right? But the two are dependent in nature. There is another graph demonstrating the same ideas, but I'm just going to rush through them. It repeats the same ideas that I mentioned to you when playing with the software. So connections, chains of causes make things dependent. Common causes make things dependent. Causal Markov condition, that's the axiom that I mentioned. It is, I think, quite uncontroversial. Some counterexamples, but there's been always a good response to the counterexamples, showing that there was something wrong with the way people framed it. In the quantum world, though, we know that this assumption doesn't hold. So in the quantum physics, we know that this doesn't hold. But there are more funny, unintuitive things in quantum physics. Again, implications. Chains of events, common causes make things dependent. Conditioning makes things dependent also when you condition on common effect or common descendant. This is the summary of the three implications. I'm going fast because I already talked about this, and I wanted to show you a few more interesting things. Conditioning also makes things independent. So when you condition on flat tire, you make the effects independent of one another. That connection to a common cause doesn't work anymore. And you break all the links. So the three causes of flat tire are independent of everything else. There's another very easy to prove theorem talking about manipulation. That has to do with interventions, with manipulation. Remember, I talked about it in the context of econometrics in the previous hour. When your intervention is perfect, the causes of that variable that you intervene on become irrelevant. The rest of the graph is just fine to predict the effects. Here's a joke that is maybe a little bit bloody. I remembered it from like 30, 40 years ago, and I kind of pulled it up. It was in Dutch, a samurai is committing a suicide, and then he discovers that he had cancer. Well, cancer is completely irrelevant because he is manipulating with the variable being alive. Yes, he's killing himself. Whether he had cancer, AIDS, and COVID is completely irrelevant now, right? He's killing himself. It's manipulating. Take a knife and cut your tire, it's going to be flat. The causes of that flat tire become irrelevant, but the effects, you can still predict the effects of that. Now, experimentation is essentially focusing on causality, on causal hypothesis. Suppose you observe correlation between smoking and lung cancer. That correlation was observed in the 19th century already. And you want to find out whether smoking is a cause of lung cancer. Here are 9 different graphs that are compatible with this correlation. The 4 on the top are graphs in which smoking causes cancer, different combinations with genetics. Probably this is the most likely graph of all. We know that there is genetic predisposition to cancer. It makes a lot of sense to have a genetic predisposition to smoking, like to drinking or to liking sweet food or liking sour food. We are born with certain preferences. So I think this is a very likely graph. But each one of these graphs is compatible with the correlation. This is a possibility. There is no direct dependence, but there is a genetic factors causing both us to smoke and to have cancer. Finally, these four are funny. I don't think they are true, but cancer may be causing smoking. You get cancer at the age of 5, and then at the age of 15 as a teenager, you discover that the itching that you felt so far goes away when you smoke. So smoking essentially makes it easier, and you smoke because you have cancer. Cancer essentially causes smoking. Again, I don't think this is true, but there's a theoretical possibility. So correlation is compatible with any of these graphs. An experiment essentially tries to eliminate graphs that are incompatible. This graph with the arcs coming from genetic factors to smoking and from cancer to smoking is like a combination of all those possible graphs in the previous slide. Manipulation. In experimental design, we use randomization. So we use a coin, by way of speaking, to decide whether a subject will be smoking or not. The coin is the only cause of smoking. If you were smoking so far, you are not smoking anymore because you get heads. If you get tails, you are a smoker, whether you like it or not. So coin is the only cause of smoking. If this is a perfect manipulation, then genes have nothing to do with your smoking, the preferences for smoking. This is no longer working. The same, the fact that you had lung cancer or not before doesn't matter because the coin decided that you are smoking. If at the end of the experiment you will see that there is a correlation between the two, it has to be because of this arc from smoking to lung cancer. And that's a 1-minute explanation of experimental design in which we manipulate, randomize, manipulate, and look for dependence between the independent variable and the dependent variable. Asbestos will only introduce noise, but it will not change the basic fact that these two are correlated with each other. There's a dependence. Of course, we cannot experiment here. Ronald Fisher, the statistician who designed this procedure, doubted until the end of his life about the fact that smoking causes cancer. By the way, people have never succeeded in the laboratory to cause cancer, as far as I know, cause lung cancer in animals. Maybe because they don't live long enough. That was really funny, a presidential debate in 1992. I'm not going to get into that because of lack of time, but it was a funny thing, and you can probably find it on YouTube if you are interested. Clear reference to causal structure and to common causes. Science by observation, that's the key here, the trick that we are talking about, causal discovery. Two classes of algorithms, of which I'm afraid I will have time to just talk about the first one. The second one is actually easier to understand. I have just 2 or 3 slides on that. The problem with it is that it's harder to understand the relationship between causality and the graphs. So it's much better to look at this class of graphs. I'll send you the entire sets of slides so you can look at that. But I'm going to talk in the last 5 minutes on the constraint search-based learning, which I think I have enough time to just show you the idea that it works. Correlation does not imply causation. You've seen it in statistic textbooks. It is true, but only in limited settings, when you have 2 variables. When you have 2 variables, that's absolutely true. You cannot establish causation. But it's not the whole truth. It is truth, only truth, but not the whole truth. In this case, of course, you have 4 cases even. The causality one or the other way, common cause or common effect observed. However, when you have the following 4 observations of dependence, the only graph that is compatible with them is this. There is no other graph, can be proven, that corresponds to those dependencies. Given, of course, the Markov assumption, which, as I said, is not controversial. If you observe these things, then you can establish causality, not only connections, but also direction of arcs. Look once again, X and Z are dependent, Y and Z are dependent. Clearly, they are connected. X and Y are independent, no common cause and no chain between them. When you condition on Z, they become dependent. The 4 patterns, this is the graph that has to be there. At the causal discovery, the foundations, there are 2 assumptions, 2 axioms. We talked about Markov condition. The connections in the graph, that's a term that I should actually remove it. This is the graph, implies independencies in data. That's what we've been doing. The second condition says, if you observe independencies in the data, they have to be reflected in the graph. And that is, unfortunately, more controversial. This is a less problematic problem, but this is more. Presence of multiple paths that cancel each other out. You stay up before an exam. On one hand, you will learn more. You improve your performance in your exam tomorrow. But on the other hand, you are going to get more tired and you'll be making maybe silly errors that will decrease your performance. It may happen that the 2 paths cancel each other precisely. They have a theorem saying that this is very unlikely. Lebesgue measures 0, but still it is a problem. So faithfulness condition is more problematic. Let's run through this quickly. The idea here is that that there are limits to what you can do with statistics. You cannot distinguish between within certain class of graphs. Look at this one, the 2. You cannot distinguish between them because what you will observe is that this variable is independent of the other 2, but that's in both, and you will observe dependence between these 2. But that's true whether their direction is this or that. So you cannot distinguish these 2 using pure statistics. And the same for each of these groups. They are indistinguishable using statistics. Let's, well, I should quickly say here. The first theorem is that there is no edge if and only if they are independent. But if you remember, we saw that in the very beginning, when we talk about Bayesian networks in independencies. That's a consequence of Markov condition, essentially. V-structure theorem is essentially those triples that where you can show that X and Z become dependent given Y, even though they were independent. How does the algorithm work? 2 stages. First is a series of tests, combinatorial number of tests of independencies in your data. And the second stage is pure logic. From these independencies, you infer what could have been the structure. First is kind of clear. The second is, there are several algorithms. Here's one. You start with a complete graph. You remove arcs that shouldn't be there. Then you find the V-structures, the second theorem that I showed you, and then you clean up. Example. I will probably end at this example because of the time. Let this be a graph that we want to discover. We don't know it, but it's there. We have data over those 4 variables. What will be observed in the data? What independencies? The first stage, remember, finding independencies. 2 arcs missing between A and B and A and D. What are the independencies? A and B clearly are going to be independent unconditionally. They are independent. No common cause, no chain. A and D, they are dependent through C. There's a chain. But if you condition on C, you'll break that path. But if you condition on C, then A and B become dependent, and then B through the arc will make D dependent. So conditioning on C alone is not enough, because then they will be dependent through B. So if you condition on B and C, then they are going to be independent. So this is the first stage. The second stage, start with a complete graph. For every independence, remove an arc. We remove this, we remove the second arc. Now we are looking for V structures. Possibilities are ACB and ACD. In the theorem, you need to have the things on the extreme independent. And they are independent. A and B are independent. Conditional on C, they are dependent, so we can orient the arc this way, the arcs. ACD. Unfortunately, to make A and D independent, you need to condition on C. So C is making them independent, not dependent. Therefore, this is not an instance of the V structure. So we need to orient this arrow in that direction to clean in the cleaning up phase. The last arc is essentially to avoid a cycle. The graphs are acyclic, so you cannot have a cycle. This arc has to be in this direction. So as you see, we have discovered that graph. I'm afraid I'm out of time. We can. It's 11:03 Eastern time, so we have been here for 2 hours and 3 minutes. Your choice. I can go longer. I can go longer without you, and we will have the recording. So, Javad, what would you like now?
How much time do you think you need, Marek, to?
I guess not much. I could wrap up in 5 minutes or 10 minutes. Your choice.
Yeah, that's very generous of you for staying longer. So we are recording the session, so if the students have to leave, they can leave. And if you don't mind, let's continue.
Okay, wonderful. Then we will go for another few minutes.
Thanks very much.
The algorithm outputs patterns. Remember this classes, equivalence classes. Sometimes the algorithm will not be able to distinguish between different cases. Then it will output patterns. Patterns are essentially of connections of two types: bidirectional arcs and undirected. Bidirectional arc means that there is a connection, but we don't know which way. The red without arcs without arrowheads means that there's an arc or there's a common cause between them. We don't know that. How do you deal with the fact that you perform many statistical tests? As you know, performing many classical statistical tests is a dangerous thing because you essentially have an increased error of type 1 and type 2 errors. Increase the probability. So what you do typically is you vary the significance level alpha from very low to very high. When it's very low, you reduce the probability of type 1 errors. When it's very high, you reduce the probability of type 2 errors. So when you're doing the discovery, you should play with that. Continuous data are not a problem at all. You just need to have an independence test. For continuous data, there is a very good independence test for the case of multivariate normal distribution. So you need to check all marginals if they are normal, all the relationships, are they linear? If they are more or less linear, you can apply those tests. So with continuous data. With mixture of continuous and discrete, the problem is that there are no classical tests of independence, so then you need to discretize the continuous data before learning. The second, now let's forget about this. Let's just a different principle, perhaps easier to understand, but there's a theorem that under ideal circumstances, this approach, even though it's completely different, based on different principles, leads to the same results. The search is essentially intractable because the number of graphs is very, very large. So what you do with this second approach is restarts, essentially, like what we do with looking for a maximum of a function numerically. We start in different positions and then you use the hill climbing, going in the gradient direction to find the maximum. I have probably mentioned all of this things already. Observation is a valid scientific method. So the people who are doing this are not only computer scientists, they are statisticians, they are philosophers who have thought very carefully about causality and why the output of these methods can be given causal interpretation. Very exciting because it's a new way of doing science that is exciting. It's not as powerful as experimentation, although sometimes it could be, but it's much less expensive because if you have data, you can draw conclusions from the data. Let me just a few minutes. Let me show you a practical study that we performed. We did that in early 1990s with the group at Carnegie Mellon philosophy department, Clark Glimmer, Peter Spirtes, and Richard Shines. PC is not personal computer, but it's Peter Clark. And they invented that algorithm. We did actually this study studying the looking for causes of student retention. Let me show you the histogram of this variable. This is the student retention in US colleges in 1992, I think. Please note that there are colleges that lose over 80% of their students in the first year. That's terrible because you need huge rooms for the first year, but the number of students in later years is much smaller. And there is a strong correlation between retention and quality of the university. How can we look at it? Rejection rate is a good indication of quality of the university. The more applicants they reject, the better they are. Look at the scatter plot. Quite visible correlation. Top universities having high rejection rate have also high retention. These are the Harvards, the MITs, the Stanfords. Carnegie Mellon was unfortunately not here in 1990s. They are probably closer here because they listened to us. What did we do? We took a data set from US News and World Report that collects the data every year from every university in US, every national university. One row is one university, and we performed learning on this using the PC algorithm. You can, by the way, enter background knowledge. The only background knowledge I would like to enter, because you have to be careful with that, data speaks harder than our knowledge. I will say that all these variables are determined at the beginning of the academic year, retention at the end of the academic year. This is the significance level for statistical tests. Here's what we get. So I'm interested in this variable. Please note that many things can be everything is correlated with this variable. But there are only two nodes that are directly related to that. Let me show you that idea that everything is correlated with everything. If I maximize it, this is the correlation matrix. You see everything is correlated with everything. In particular, retention rate, correlations are really far from zero. So it's in general not straightforward to be able to say what is directly related, what is causing the things. This is what we get with 0.05 significance level. We should play with that significance level. Let's make it very small. 1 in a billion, let's say. I'm still getting a strong relation, well, one that reminded. It was very difficult to reject null hypothesis, which is independence. It was still rejected here in this case. And in this case, top 10 is the high school standing. These are the average standardized scores, SATs, pretty much like entrance exams to college. These two are correlated highly because they are testifying of the quality of students. When you play with this significance level, let's make it absurdly high. Now I'm reducing the probability of type 2 errors. Look, it's very easy to reject independence. Still, independence wasn't rejected in all cases. So we can trust that this variable, for example, this is the only way it connects to the rest. The rest was independence. Even though we could reject it very easily, we didn't reject it. So at most 3 of these variables directly related. And we notice that at the significance level of 0.02, I think, only this remains. Our conclusion was quality of incoming students expressed by these 2 variables is the only thing that influences retention. Retention wasn't academic. People left because of many other reasons. We wrote up our conclusions. They listened to us, and they conducted an experiment. They changed the admission criteria, offered partial stipends to the students, to the applicants with the highest SAT scores, and they observed increased retention a year later. So I think Carnegie Mellon, if they followed this up with refining the admission policy, they're probably now closer to the top in terms of the student retention. That's all I wanted to show you. Do you have any questions?